we're going to be proving more in detail that the axiom of completion distinguishes the real numbers from the rationals. Or in other words, there are gaps in the rational numbers. Shouldn't take a genius to figure that out. For example, pi, e, and the square root of 2 are all in the reals, but they are not in the rationals. So, however, how do we actually express one of these gaps? So let's say we're talking about e, for example. Well, no, I don't know that many digits of e. So let's go with pi. Know a few digits of it, 3.1415926535897. Pretty long. I know there are people out there who beat me, but yeah. So, for example, let's say we had an interval from 3 to 4 that contains pi. So then we have another guy who makes an interval and says, I have it more accurate than you. Actually, I've narrowed it down to between 3.1 and 3.2. Yes, very accurate and to scale, I know. And then we have another guy who comes in and says, well, actually, it's not between 3.1 and 3.2. Narrowed it down even further to 3.14 and 3.15. Then another guy walks in and says, you fool. How have you not realized that it's between 3.141 and 3.142? Then another guy walks in and says, why are so many of you people in here? Anyway, I figured out that its pi is somewhere in between 3.1414 or 3.1415, 3.1416. And then more and more people keep walking into the bar until the bar is infinite. It's an infinite bar. Drink to your heart's content. So, then, what are these infinite intervals? Well, essentially, we can say that the limit of all these intervals, if we're taking it over the rational numbers, because obviously all of these numbers that those dumb pi approximators were talking about, they're all rational numbers, but the limit of all of these is going to be the empty set. Not going to be pi, because that's not in the rationals. So there's a big fat gap. But that does not happen in the real numbers. So essentially, we can't say limit yet because we haven't figured out what that exactly means. So instead, we're going to say the intersection of all the sets because that has a much simpler meaning. If x is in the intersection of a and b, that means that x is in a and x is in b. So we can have the intersections of all these sets. Let's say this is A1 and this is B1. This is A2 and this is B2. This is A3 and this is B3. By the way, I've picked these approximations out intentionally so that the upper bounds and lower bounds have the same decimal number of decimal digits. So it's easier to tell what cell is which cell. So we have n equals 1 to infinity of the intersections of all these intervals. So in the real number, so we want to prove that in the real numbers, this is never going to be equal to the empty set if we have that I1 is a superset of I2, which is a superset of I3, and so forth. Yeah, everyone, my name is Saborno Isaac Berry from Hunter College. So here I'm taking real analysis, and today I'm going to be talking about some new concepts that we learned. All right. So first of all, let's go over a bit of what we reviewed yesterday, which was mostly the axiom of completion, as well as the infimum and the supremum. So for example, if you have the set 0, 1 exclusive, then they're not really a maximum or minimum. You might say 1 and the minimum is 0, but 1 and 0 are not in the set. By definition, maximum and minimum have to be inside the set. But an infimum and a supremum don't have to be. their official terminology is the infimum is left as an exercise for the reader, as it was for me. So the supremum is essentially the least upper bound. So in other words, it is one in upper bound, which means for all A inside the set that we're talking about. So let's say S. The supremum, which let's say is some number X, is greater than A. And number two, for so number two, for some other lower upper bound B, which satisfies condition 1, then X is always less than or equal to B. Alright, good. So now, let's move on. And also the axiom of completion essentially states that anything that is bounded above, i.e., let's say we have this set right over here, S, anything that is bounded above, for example, S is bounded above because this dot right over here is to the right of every single element, so it's upper bound for S. Every set that is bounded above has a supremum, or a least upper bound. And that supremum could, for example, be right over here. So everything that has an upper bound has a least upper bound. Really important to know. So this distinguishes the reals from the rationals. I believe we did that last time. So let's actually move on to day number 2. So today we're going to start talking about like a more official definition of the supremum. So essentially what we're going to say is that for some set, call it S, just like so, if we have the supremum X right over here, then let's say we decrease it by a teeny tiny amount, like epsilon or dx or h or whatever you feel comfortable with, but our textbook uses epsilon, so we'll go with that. So essentially the supremum is defined such that for any epsilon that is greater than 0, x minus epsilon is less than some element of the set. Now you might say, why not just say that x minus epsilon is in the set? Well, because that's not necessarily true. For example, let's say we have the set 1, 2, 3, 4, 5.5. Then the supremum of this doesn't take a genius to realize that the supremum is 5.5. So then, let's say our epsilon was 0.1, some really small amount. Then we get 5.4. Is that less than one of the elements? Sure it is. But is it an element of the set in itself? No. So we cannot say that. So this is an incorrect notion. So x minus epsilon is, there exists some element A inside our set S such that x minus epsilon is less than A. Here is our definition of a supremum, where x is our supremum. And an infimum can be defined very similarly. So all you really have to do is change this to a plus and make this a greater sign. It's essentially almost the same exact kind of thing. So we're also going to start talking about negating statements. And this is just very important, not as an actual concept in itself, but in general for writing proofs. So if we have a statement, like for example, the statement my professor used is the upper bound, so x is an upper bound of S, if for all A in S, X is greater than or equal to A. So now how would we negate that? Well, negating for all tends to make it turn into there exists and vice versa. So how would we show that right over here? Well, X is not an upper bound if there exists an exception. So for all, if we negate it, that means there exists an exception to the for all rule. Hope that helps you understand why they're like negations of each other. If there exists an A in S such that X is less than A. Good. So what this would say in layman's terms is X is not an upper bound of our set if there's an element of the set of which is greater than our upper bound. So that's how we can negate statements. That's a very important thing in terms of proof terminology. So now, let's get to the main meat of the lesson. So let me a conditional proof. Oh, this actually makes it a little bit harder to write. Conditional proof. So what does that mean? Well, often you'll see the term if and only if abbreviated as IFF. So that means you have two prongs of the proof you have to solve for. If P if Q and P only if Q. So essentially here what we're testing is Q, because if Q is right, then P is right. And here what we're testing is P, because if P exists, then Q exists as well. So for example, it is a square if it is, okay, so let's see. So for example, P could be, it is a rectangle if Q could be a square, but that wouldn't satisfy the only if prong. So here is an example of such a biconditional proof. So assume that we have some number S in the reals. No, this made it worse, definitely. In the reals, okay, such that for A is a subset of the reals. So S is then the supremum of A if and only if there exists some epsilon greater than 0. For all epsilon is greater than 0, there exists A in A such that. So this is the supremum definition that I gave you a while ago, around the beginning of the lecture, and now we have to prove it using two proofs in one. So like this. First we have to prove if S is the supremum, if S really is the supremum, then there exists that epsilon such that if this, prove this, for all epsilon is greater than 0, A with, or such that S minus E is less than A. Sorry, I'm stumbling over myself here. I should know this by heart. So, prove that for all epsilon is greater than 0, such that there exists an A in our set big A, such that S minus epsilon is less than that element. So, how would we prove something like that? Well, we just use our normal procedures. So, we we know that since S is the supremum, which is given to us, anything less than S can't be an upper bound because the supremum is the least upper bound. Since we have S minus epsilon and epsilon is greater than 0, that means S minus epsilon is less than S, so it's not an upper bound. Okay, cool. So then, by the negation of the upper bound that we did before, there is basically just a carbon copy of this statement. There exists an A in our set such that S minus epsilon is greater than A. Okay, that's one half done. So then, the second half is if we have all this gobbledygook, so there exists an A in A such that for all epsilon is greater than 0. Okay, let me see. There exists, okay, for all epsilon greater than 0, there exists an A in our set big A satisfying S minus this epsilon is less than A, then this number S that we have is the supremum of our set big A. So this is what we call the necessary proof. This is the sufficient proof. So this is what we have to prove, and this is what we're given. So this is a little bit of a longer proof, so I'm going to coast through it really quick. So suppose for all epsilon is greater than 0, we have the existence of A, which is an element of big A. So such that S minus epsilon is less than A. So let's suppose this, which is just our initial assumption. So then we assume that S is an upper bound in, well, the question that we were trying to solve for. S is an upper bound. So that's one part of our proof of the supremum from last time done. Now we just have to prove that it's the smallest upper bound. So let's say proof by contradiction. We have some bound B which is even smaller than S. However, that means that there would exist exactly one epsilon which is greater than 0, such that S minus that epsilon is equal to B, because B has to be less than S, so it falls within this space. So, since S minus E can never be an upper bound, no matter what epsilon you choose, then B can never be an upper bound either, QED. So that means S is our lowest upper bound. Great, so that's what we call a biconditional proof. Now for the, how much time do we have left? So I'm going to keep going over here. So now what we're going to do is something very important. No, actually, if we have 1 over n, such that n is in the natural numbers, this set, I was supposed to tell you why the infimum of this is equal to 0. But we never have a proof until now. So here is what we call the Archimedean property. So let's say we have some number which is y, and y is less than 1 over n for all n. And that's the spooky, mysterious, irrational number that we said might have existed last time. So now we're going to prove that thing right there does not exist. So now we're going to define some number x as 1 divided by y. So y is in the real numbers, by the way. It has to be for this proof. So, does there exist some x such that x is greater than n for all n in the natural numbers? So what this is essentially saying is, is there a number in the real numbers which is greater than every single natural number? And the answer is pretty obviously no. But unfortunately, we can't just say proof by opinion, no. That's not how proofs work. So, unfortunately, we actually have to get through this. So, here's what we want to prove. The Archimedean property, which I'll go back to the beginning right over here and erase this. Archimedean property. Sorry, this theorem is pretty long, so I'll be locked into my notebook for this one. So, the Archimedean property, number one, there does not exist an x in the real numbers that is greater than every natural number. Or the negation of that statement, which is what we're going to be doing in this class most of the time. For any x in the reals, there exists some number n in the naturals such that n is greater than x. And number two, which is going to be a corollary of number one, which we'll find out soon enough, there exists an n in the naturals such that 1 over n is less than y for all y. Oh, wait, no, wait. Okay. For some y in the positive reals. Okay, so now this first one is not the hardest thing to prove, honestly. So let's prove it by contradiction. Let's say it was true. So we have that x is greater than every single natural number, or the negation of this statement. There exists an x in the reals such that for all n in n, the naturals, x is greater than n. So now this implies, since x would be an upper bound for the naturals, this implies the existence of a supremum of all natural numbers. And we'll call that imaginary number alpha. So then, if alpha is the supremum, that would imply alpha minus epsilon is less than one element of the set. So let's say our epsilon is, for example, 1. So alpha minus 1 is less than some element of the set n. Wait, but what would that mean? If n is in the naturals, n plus 1 is in the naturals, obviously, right? Because it's the counting numbers. But wait a second, if we add 1 to both sides of this inequality, we get that our supposed supremum is less than one of the elements that we're looking for. So this can't work. Storming outside? That's not good. So that means that number 1 is proved. I mean, pretty obvious, right? Well, not the proof, but I mean by intuition. Number 2 is just a direct corollary following over from that. So essentially, we have that y is just equal to x is equal to 1 over y, which is what we're going to say over here. So a 1 over, for all 1 over y in R, there exists an n such that n is greater than 1 over y. But wait a second, what would that mean? That means if we multiply both sides by y, we get yn is greater than 1. We divide again, we get y is greater than 1 over n, or there is some 1 over n that is less than y. So that means this mysterious irrational number, which we said was between 0 and the last element in our set, doesn't exist, because there's another element after that which is smaller. So that means that we've proved it, that the infimum of the set 1 over n such that n is in the naturals is 0. Alright, there it is. See you in lecture number 3. Essentially the essence of the proof of our theorem 1.4.1 in our textbook. So essentially we have that definition of x being into the intersection of a and b. So essentially from that we can derive that x has to be in every single set in for all n in the naturals. Okay, cool. So we can essentially show that x is the supremum of A. How do we even know it has a supremum? Or by the axiom of completion. We know it's bounded above because think about our approximation from before. This is A1 and this is B1. This is 3 and this is 4. A2 and B2 get even closer to the center. So these are the farthest out we're going to go. Now, obviously, Bn is always greater than An. Now, there's a proof that goes more in detail, showing that for all m and n in the reals, Bm is always greater than An, no matter m and n's relationship individually. But that's not something I want to go over right now. Maybe tomorrow. So, as we get closer and closer and closer to the center, eventually x lies right over here, so it's the supremum of A. Since A is bounded above by one of these guys, like B1, then it has a supremum by the axiom of completion. That supremum is x. So we want to show that for all n in the naturals, an is less than or equal to x, which is already covered by this, but then we have x is less than or equal to bn. So we essentially want to show that it's the infimum of bn. And that's what this proof goes on to show. And that is essentially how we can prove that x is going to be in the middle of all of this. And thus, since x is in every single set, that means that the intersection of all of them at least contains x. So yeah, that's it.